Gamers appreciate premium, immersive experiences. But with more opportunities than ever to expand your audience beyond phones and reach players on Android tablets, foldables, desktops, and Chromebooks, what does it take for your game to stand out? Today, let's learn the best practices for asset management, windowing, and graphics processing to build quality experiences and impress your players across form factors. My name is Daniel Levy, and I'm a developer relations engineer on Android large screen gaming.
My name is Patrick Martin. I'm a developer relations engineer on Google Play Games on PC.
And I'm Matt Monasch, a developer relations engineer on ChromeOS.
To get started, let's dive right in and learn the best practices to level up your game across form factors.
Your game assets are the pride and joy that your artists and designers painstakingly authored. So, it would be such a shame to have put all that work in just for your game to not look as great as possible. So, whether your players are on a phone, a tablet, a foldable, a laptop, or using an external monitor, we are here to help make sure your assets shine. Android has always had a vast array of device models that players might game on. Historically, this has meant various different hardware capabilities, but typically only two kinds of screens: smaller phone screens and larger tablet screens. These days, hardware capabilities now range from budget chips with no discrete GPUs to devices capable of running cutting-edge AAA games without breaking a sweat. Also, phones have now expanded into larger tablet-like screens with foldables, and there are larger wide aspect ratio screens on laptops and with monitors. With all this complexity, how are you supposed to manage which assets to use? The answer? Be flexible. But to do that, we first need to understand the device and the display. CPU, GPU, and RAM, of course, are the important hardware aspects to query for, and you can get those by identifying the SoC and hitting the Activity Manager for memory info. For your display, the resolution can be fetched through the Display Metrics API. Once you have these values, you can make the best choice for what assets to use and what graphical options are best for that player. Remember, this is a balance. You want to provide the best visual experience, which means weighing graphical fidelity against performance. Consider that loading higher resolution game assets requires more memory and more processing to display. However, you should try to use higher fidelity assets on larger and lower density screens to provide the most immersive experience for your players and avoid game assets from being pixelated. The same is true for your text assets as well. Blurry and tiny text assets are a surefire way to stymie your retention. Conversely, feel free to use lower fidelity assets on high definition small screens. The higher density of these screens means that there will be a much smaller scaling factor, so even lower fidelity assets can end up looking crisp. If you're thinking that not all players have the same visual preferences, well, you're right, and this is why we also recommend that you provide graphics toggles in your settings. This is quite common in other environments that have variable player hardware, like in PC gaming. One of the worst experiences a gamer can have is to get a brand new device, load up their favorite game, and then discover it's now pixelated or otherwise suboptimal. Ensure that you have appropriate default level of quality settings for all supported devices in your device catalog, and regularly update your game with default settings when new devices are released. Additionally, consider having broad quality tiers like low, medium, and high that apply when your quality system doesn't have a rule for a specific device. You can use the device RAM, SoC, and resolution as a heuristic to approximate device tier. Consider also that more complex shaders and post-processing effects like anti-aliasing are more taxing for a device. Profile your game's rendering and also test out to see what effects make the biggest difference, both in performance and visual senses. By doing this, you'll provide a great experience for most players while affording your more discerning and particular players a way to customize their experience. Beyond asset quality, also consider the texture compression format that gets sent to the device. The underlying hardware for these Android surfaces have a few variations that impact algorithm performance. If you're not particularly worried about performance and want to keep things simple, use ASTC assets. It might be slower on some devices, like on Windows, where there will be a translation layer that converts the assets on the fly to a supported format, but it'll get the job done, and you'll save yourself the overhead of dealing with multiple asset packages for different compression types. ASTC works well with GLES and Vulkan alike, so no matter the graphics language, you'll be covered here. For maximum compatibility on very old devices, if your performance and storage size isn't a large consideration, just use ETC2. Otherwise, if you're looking to get the best performance and visuals possible on those large screens, use DXT for Google Play games on PC and Chromebooks that run on x86, and then fall back to ASTC in all other cases. You can also use Play Asset Delivery to ensure that the right version of the assets gets sent to the device. Now, let's hear what Daniel has to say about windowing and resizing.
When you're building for multiple form factors, your surface is more than just a single screen. Your game runs in a window that can dynamically resize. For example, on fold and unfold, on rotation, in split screen mode, or in multi-window mode on ChromeOS. Additionally, device features like display cutouts and hinges may even extend into your window. By dynamically handling configuration changes, you can provide the best experience for your players. Let's expand our knowledge and learn more about resizability. For Google Play games on PC, the platform handles window resizability while respecting the specified aspect ratio, and the window size is locked to the optimal dimensions automatically. At a minimum, you should support 16:9 aspect ratio if your primary orientation is landscape, and 9:16 for portrait. But for the best experience, support 21:9, 16:10, and 3:2 aspect ratios for a landscape game. On ChromeOS and new Android tablets and foldables, your game may run in configurations like split screen mode or freeform multi-window mode that you might not already handle. With freeform multi-window mode on ChromeOS, the initial window dimensions become an important consideration. Either declare the default layout to control the initial window launch dimensions, or set the minimum width and height to prevent your players from resizing the game window into dimensions you don't support. Set the gravity attribute to determine where on the screen the window appears when launched. Alternatively, use dynamic launch bounds to set the starting window dimensions. On Android, if your game doesn't support all window size and orientation changes, the platform letterboxes your game in compatibility mode. When a player moves to an unsupported configuration, they might be prompted with an option to reload the game and recreate the activity to best fit the new window size, which can be disruptive to the player experience. To get out of compatibility mode, declare that your game can handle resizability, avoid aspect ratio and orientation restrictions, and declare support for all configuration change events that can occur on window resize. Next, handle the configuration event and check the new window density, width, and height. You can also query the window manager for the current orientation. Now that we have this metadata, let's put it to good use. For the best experience, make full use of the new window size. Anchor your user interface elements relative to the edges of the window so that they can dynamically adjust when the window size changes. Ensure your camera, field of view, and aspect ratio adjust to both fill the full window and avoid distorting your game assets. Identify key gameplay assets, for example, the player character and their environment, and ensure that you mitigate any aspect ratio dependency. You could dynamically scale these assets or adjust the camera to fit the new window in cases where key gameplay content could become cut off, like on change from landscape to portrait. Additionally, consider alternate UI layouts that make good use of different aspect ratios. If, however, your game has some aspect ratio dependency, use the new dimensions to set your camera to render to the full window, but letterbox and fit to the best aspect ratio to avoid distorting your game. Consider still anchoring your game UI to the edges of the window. You could even add a backdrop treatment to make use of the additional blank space afforded by letterboxing your core game content. Now that your game is able to handle window resizability for foldables, free-form multi-window, and split-screen mode, let's learn how to handle display features that can extend into your window. First, some important news. Starting in Android 15, your app will be edge-to-edge by default, and the system bars will be translucent or transparent by default. You can learn more about this change in the I/O workshop, Improve the User Experience of Your Android App. So, to provide the most immersive experience for your players and avoid system UI like status or navigation bar extending into your game window, use the Window Insets controller to set full screen immersive mode and render your game to the full window extent. Next, set the display cutout mode to always, which renders your game behind display cutouts without any system padding to make the best use of the full screen. Display cutouts can occur in many different shapes, sizes, and even move with respect to your window on orientation change or on fold and unfold. To handle this, you'll want to either add a view layout change listener or update your configuration handler to query the Window Insets API for any display cutouts. You can use the display cutout bounding box to determine how you might want to adjust your UI positioning to avoid a display cutout occluding critical game functionality. Now, let's learn more about foldable devices. According to Counterpoint Research, global shipments for foldable devices are expected to cross 100 million by 2027. So, to expand your audience, increase player immersion, and really level up your game, consider using the Jetpack Window Manager library to add support for dynamic layouts on new foldable devices. Jetpack Window Manager contains the folding feature class, which describes a fold in a flexible display or a hinge between two display panels. Similar to how we handle display cutouts, check the bounds and occlusion type of any folding features to determine if you should reflow any critical game content. Putting this all together, we can determine when a foldable device is half opened and check the folding feature bounds to draw two separate logical views in a game. You could keep the main gameplay content on the top view and add a virtual gamepad, map, player chat, or even inventory management to the bottom view to enhance player immersion. With that, let's learn the graphics processing best practices from Patrick.
So now that we're thinking about these large screen devices, let's talk about how you can step up the immersion. You're no longer holding a little viewport in the palm of your hand. You have this giant window into another world. The immersion isn't as great if your game is dull and drab. Use as much of the human visual color spectrum as possible and ensure that vivid colors are rendered properly while also maximizing contrast and brightness on HDR displays to improve realism and immersion for your players. On Android, a device with a P3 color space extension will let you render to a wide gamut color buffer, making your game really stand out and pop. You can check for this in your own custom renderer or look for the HDR button in your game engine of choice. To load a wide color bitmap, the texture should use a color profile wider than sRGB, like Adobe RGB, DCI P3, and Display P3. So when authoring your game textures, be sure to embed the wide color profile directly and test on an HDR display. Next, let's make your game run smoothly. Look at this diagram. This is a diagram for a game running at a pleasantly consistent frame rate, allowing a player's brain to pick up on smooth motion, maybe super smooth if you're going at 120 Hz, but 30 is still fine. Now you jam this game into a high-end PC, it renders so much faster and stutters? Look here, the application row has render C going really fast. It kicks B out early, and time appears to speed up for a second as C gets 3 frames before a more normal D frame. Let's take a look at another common issue. You may recall Matt mentioning the need to profile complex graphical effects. To that end, you may have followed advice so far. You probably have wonderful high-resolution textures and fancy surface shaders, Great high poly models, maybe you've bumped up your render resolution. Now you drop the game onto a large screen tablet with the same SoC as a phone, but higher resolution display, just more pixels to drive. In this graphic, if you look at application row, frame B pushes into C's time frame, so it takes the longest time to build, causes A to show for an extra frame, then it gets half its regular time to display before C appears, which started rendering late. Time's going to feel like an accordion to a player in this case. Definitely not smooth. Enter Swappy, or the frame pacing library if you want to sound fancy. A library designed specifically to handle frame coordination on Android mobile devices to deliver frames consistently on time with improved battery life. Remember when we rendered too quickly? Swappy helps you delay rendering D until B gets its time in the sun or on screen. And when you had that extra long frame, Swappy can't turn back real time, so frame A still stays on a few milliseconds longer, but now B and C get equal frame times, and C's rendering isn't bumped up right up to B, so you have a more fixed game time step between them. Swappy can help you by maintaining a target frame rate, or even help you choose the right one on the fly. Building for Vulkan allows you to take full advantage of the graphical capabilities of modern Android devices. If you're using a game engine, this means that now is a great time to check that Vulkan checkbox and assess your game's performance. Now, if you're rolling your own engine, as a good number of y'all do, the Vulkan transition might be a little intense, but I have some advice to help you out. For example, as Daniel mentioned earlier, games resize now on most large screen devices. It turns out that players really like to play an idle game while watching a movie or checking on their group chat when competing online. And Android does its best to work for these folks. What this means on the Vulkan side is that your swap chain needs to get torn up and recreated as players find their perfect feng shui layout. Basically, what happens is you call VK acquire next image KHR to start rendering, but get a result that indicates out of date or suboptimal. This tells you that it's time to rebuild, as you did at game launch, and you can happily continue rendering. You should check out AGDK Tunnel from the Android Game Samples repo to see how this is done. A little more work than calling GL Viewport and recomputing a projection matrix, but it's a small price to pay for the improved performance and control of Vulkan. Now, another thing to consider is that Android devices have varying architectures. For example, a phone or tablet typically has an SoC with memory shared between the CPU and the GPU, and game developers take advantage of this when loading things like textures into GPU memory. But when you go to PC, suddenly the GPU is hanging out on the end of a PCIe bus with its own bit of graphics memory. If you're using a feature like host visible device local memory, which probably always works on mobile devices, you may need to query for the feature and have fallbacks on PC-like devices. This is part of the greater control in Vulkan. It's clear when and how memory can be read or written. In addition to being faster and more predictable, Vulkan has another fun party trick: ray tracing. No longer relegated to drawing reflective spheres above checkerboard ground planes on workstations, devices are hitting the market now with ray tracing support. But the necessary extensions are only available on Vulkan and can really make your game shine. Back on over to Matt to close us out.
To recap, today we learned the importance of being flexible with your game assets and ensuring that you have both high-quality assets for large screen devices and a robust level of quality system to balance quality and performance trade-offs. We also learned how to build great resizability support while gracefully handling device features like display cutouts and folding features to best immerse your players. And finally, we saw how you can use frame pacing to provide smoother gameplay, enable HDR for better immersion, and how to adapt to the changing mobile landscape with the transition from OpenGL to Vulkan. Thanks again for joining us to learn about the best practices for asset management, windowing, and graphics processing to build quality experiences across form factors. We look forward to seeing how you can level up your game.